Hey there guys, welcome to the video. My name is Pushpinder Gill, and in this video we're going to be talking more about probability distributions. In fact, we're going to be talking about a specific type of probability distribution which is known as the Bernoulli trials. So this is how the way this is spelled, right? So what is known as a Bernoulli's trial, or let's say, what is known, how does a trial fall under the category of Bernoulli? There are few properties, certain aspects that are associated with every trial. So if a particular trial has these properties, the following properties, then it's supposed to be known as a Bernoulli's trial. So what are those specific properties? So the first property is that there should be finite number of trials, right? So there should be finite number of trials. Let's suppose one of the classic example is me flipping a coin. Let's suppose I'm tossing a coin, and I'm tossing a coin, let's say 10 times. That means I'm tossing the coins a finite number of times. That means, it's actually satisfying the criteria of it being a Bernoulli trial. The second characteristic which is important, that the trials should be independent of each other. So the trials should be independent of each other. So when I say independent, I mean to say that the outcome of one trial should not at all affect the outcome of the other trial. So let's suppose if I'm flipping the first coin the first time, when I'm flipping the same coin second time, the outcome should not by any means depend upon the outcome of the previous or the coming trials. So that means the trials are completely independent of each other. And one of the most important characteristic of a Bernoulli trial is there are only two types of outcomes. So there are only two outcomes, and we call them success or failure, right? So there are only two types of outcomes, success or failure. In the same case, when we toss a coin, there are only two types of outcomes. There is either a head or there is either a tail. So if you're playing a game wherein if head turns up, then you win the game, then head is a success and tail is a failure. Well, you don't need to always name them success or failure. All we need is that it's supposed to be a trial with only two outcomes, and we just call those outcomes as success or failure. And it need not to be that the probability of success should be equal to the probability of failure. They can be different as well. However, the probability of success and the probability of failure should add up to 1, because there is no other trial. So that is actually a very, very important case. And the next case is that the probability of success, that is the probability of success, remains the same in each trial. So as I said, the probability of success will remain the same in each trial. The probability of failure will remain the same in each trial. It's not always sure that the probability of success will be equal to the probability of failure. That is not always true, but the probability of success in each trial would remain the same, and the probability of failure in each trial will remain the same. And success plus failure will always add up to 1. So I've already talked about a lot of things over here. That is a Bernoulli trial, and these are the 4 characteristics of a Bernoulli trial that should be there when if a trial is supposed to be called as a Bernoulli trial. Now let's go ahead and see this question over here. So the question says that a bag has 6 white and 4 red balls, and so the question says that tell whether or not the trials of drawing 4 balls are Bernoulli trials. After each draw, the ball drawn is replaced or it's not replaced. So I have 2 kinds of probabilities: when the ball is replaced and when the ball is not replaced. Now we have to check whether they are meeting the criteria of being a Bernoulli trial or not. So the first criteria is that there should be finite number of trials. So are there finite number of trials? Yes, they are, because in both the cases there are just 4 trials. We are actually drawing 4 balls only. So it's meeting this, both are meeting the first criteria. And the second criteria is that the trials should be independent. Now let's see whether the trials are independent or not. So what's the probability? Again, there are only 2 outcomes also. There are only 2 outcomes, Either you'll get a white ball or you'll get a red ball. So what's the probability of getting a white ball first in this case? That is going to be equal to 6 by 10. And what's the probability of getting a white ball here? That is again 6 by 10. Now what about getting the probability of getting the white ball again? Now since I'm replacing the ball, that means I'm putting the ball back again into the box, the probability is again going to be 6 by 10. However, over here, when I draw another white ball, let's say the second white ball, the probability, it's not going to be 6 by 10 because I'm not replacing the ball, so the probability would actually be equal to 5 by 9. That means it is not meeting the criteria that the probability of success or probability of one kind should be same throughout the question or throughout the trials. That is not met here, which means this trial is not a Bernoulli's trial and this trial is a Bernoulli's trial. Right? Now why is that? Because the probability of, let's say, you getting a white ball is a success. So the probability of success in each trial is different here, which means that this is not a Bernoulli's trial because this is not meeting the criteria of a Bernoulli's trial. So suppose you're understanding this point over here. Now let's see something interesting in a Bernoulli's trial. Let's suppose if I'm tossing a coin, or let's suppose there are I'm performing 3 trials in a Bernoulli's trial. I'm performing 3 trials. So either I can get a success or I can get a failure. So if I'm performing 3 trials and the sample space is actually going to be either it would be all success or it would be 2 success and 1 failure, or it can be, since the third one is a failure, the second one can be failure or the first one can be failure. Then again you can have 1 success and 2 failures, then just the second one can be success or the third one can be success, and then you're going to have all failures. So how many cases are there? There are going to be total of 3, 4, 5, 6, 7 and 8 cases. So there are total of 8 cases when you have 3 different trials of success or failure. Right? Now let me try and do one thing here. What's the probability of getting no success at all? Right? So what's the probability of getting no success at all? So that will actually be equal to probability of getting all the failures. Right? So that is actually equal to probability of getting all the failures, which is equal to probability of failure into probability of failure into probability of failure. And again, let's say one more thing is that the probability of success is actually equal to P and the probability of failure is actually equal to Q. So probability of not getting any success will actually be equal to Q times Q times Q. So that is actually going to be equal to Q cube. And what about getting the probability of being successful one time? That will actually be equal to probability of, this being successful one time will actually mean just being successful one time. That would mean this case, and this case here. These are the 3 cases that I have to consider. That is SFF, that is FSF, and that is FFS. So if I want to find the probabilities here, so what I'll have to do is I'll have to find the individual probabilities and add them up. So over here the probability is going to be Q into P. So it's going to be PQ square, again PQ square, and again PQ square. Because the probability of failure is Q, probability of failure is Q, and probability of success is P. So this, if I add these probabilities up, so the total probability is going to come down to 3PQ square. And what about getting the probability of 2 successes? So in that case, again, now if I just be a little quick here, all I have to do is I just have to add these probabilities, right? So all I have to do is I just have to add these probabilities. So that will actually come down to be equal to P square Q, P square Q, and P square Q. So the probability is going to be equal to 3P square Q. And the last case is getting all 3 successes would actually mean probability of getting a success, success, and success, which is actually equal to P cube. Now if I try to, let's say if I try to find out the overall probability, or if I say, let's suppose we try to observe its probability distribution, this is how the probability distribution is going to be. First of all, it's your random variable x. What all different values it can take? X being success. Success can have no success, one time success, two times success, or three times success. When it's no success at all, the probability it's q cube. When there is a success, the probability is 3pq square. And when you have two successes, the probability is 3p square q. And when there are three successes, the probability is pq. And if you have watched, all the basic math videos, you would actually observe this here. What is happening here? First, you had nothing but 1 into q cube, which is nothing but 3c0 into q cube into p raised to the power 0. And what about this here? That is actually equal to 3c1, this case over here, into p to the power 1 into q square. And then you again have 3c2 into p square into q. And over here you have nothing but 3c3 into p to the power 3 into q to the power 0. What is this? This is nothing but a normal distribution. What is this? This is nothing but the normal distribution, which means I can say that the trials of a Bernoulli theorem, the trials of a Bernoulli trial follow the distribution. The probability distribution is distributed normally. So the normal distribution has some kind of a connection with a Bernoulli's trial. Let me just go ahead and generalize that. Let's suppose if I say we have a Bernoulli's trial. We have a Bernoulli's trial with n different trials. We have n different trials, and let's suppose the probability of success is p. Let's say the probability of success is p, and the probability of failure is q. And we know that the probability of success and failure is actually equal to 1. And this is how the probability is going to look like. So if I say that the value of x, that is the probability of probability of success, it can actually take a lot of values. It can take a value 0, it can take a value 1, it can take a value 2, it can take a value 3, all the way till n. So when it takes a value 0, what is going to be the probability distribution of it here? So that is actually going to be equal to nc0 into, since you have no success at all, so you're going to have all failures, that is q to the power n into p to the power 0. And what about the first case? That's going to be nc1 into q to the power n minus 1 into p to the power 1. And what about here? That is going to be nc2 into q to the power n minus 2 into p to the power 2, and so on it goes till n terms. So it's going to be ncn into q to the power 0 and p to the power n. So that means my Bernoulli's trial are going to follow normal distribution. So the probability distribution of a Bernoulli's trial is going to be a normal distribution. So suppose you're understanding this point over here, guys. So that means this is nothing but, this over here is nothing but an expansion of p plus q all the way raised to the power n. And since we already know that p plus q is actually equal to 1, that means if I add all the probabilities here, the sum is actually going to come down as 1. So if I want to find the nth, let's say, if I want to find the nth term of a probability distribution, let's suppose in a Bernoulli's theorem, I want to find the probability of success being equal to x. Let's suppose I want to find x successes, then that is actually going to be equal to ncx into q to the power n minus x into p to the power x. So that is actually going to be the any nth term, any x term of a Bernoulli's theorem, where x being the number of successes. As you can clearly see, the more the number of successes, the more should be the probability, the more should be the power of p. So that is actually given over here. Now how do you use that? How do you use that in your practical terms? Let's suppose if I want to say that I'm tossing a coin. If we toss a coin, what's the probability of getting, let's say, if I toss a coin, let's say 6 times, what's the probability of getting exactly 3 heads? So what is the probability of getting exactly 3 heads? Now over here, again, it's actually a Bernoulli's trial, because tossing a coin is always a Bernoulli's trial, because you have only two outcomes, head and tail, and the probability of heads is same in all trials and the probability of tails is also same in the all trials. So that means all you need is you need the probability of heads, number of heads, to be equal to 3, which is actually going to be equal to the number of trials are 6, which is actually going to be equal to 6c3 into the probability of head raised to the power 3, 6 minus 3, or let's say 3, into probability of tail raised to the power 6 minus 3, something that we have actually used here, this over here. And in that case, if I try to solve it, the probability of getting exactly 3 heads is going to be equal to this. And I suppose you know that is nothing but 6 factorial divided by 3 factorial into 6 minus 3, 3 factorial, into what is the probability of getting a head, that is 1 by 2 raised to the power 3 into 1 by 2 raised to the power 3. So if you were to do it in a subjective way or in your class 12 examinations, this is the way to do it. But if it's actually an objective question wherein you're given answer options, what is the probability of getting 3 heads and 3 tails? So that actually equal to the individual probabilities, 1 by 2 raised to the power 6, that is 1 by 2, 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 into 6 factorial divided by 3 factorial into 3 factorial. That is actually the number of ways this HHHTTT can arrange itself. So you should go and watch the probability of complex events if you want to understand difficult questions to be solved using this theorem over here. This is actually very, very, very important towards the using the probability in practical terms. So let's go ahead and use another example. Let's suppose if I have a question and the question is, so let's see this question here. So the question says that 10 eggs are drawn successively with replacement from a lot containing 10% defective eggs. So the question says that find the probability that there is at least one defective egg. So we're supposed to find the probability that there is at least one defective egg. So the probability of getting at least one defective egg will actually be equal to 1 minus the probability of getting no defective egg. Right, because at least one defective means minimum one defective. So you can either calculate the probability of getting 1 defective, 2 defective, 3 defective, 4 defective, 5 defective, or whichever way you want to do it. Or the better way to do this question is that probability of getting at least one defective egg is actually equal to 1 minus probability of not getting any defective egg. So what is the probability of getting no defective eggs? So that means what is the probability of the number of defective eggs to be actually equal to 0? So that is going to be equal to 1 minus what's the probability of getting number of defective eggs to be equal to 0, and we have that the number of trials are actually 10. So it's going to be 10C0 into and we know that the eggs being defective here are a success and eggs being not defective here are a failure. So the probability of getting the defective egg is going to get multiplied by the probability of not getting defective egg, and we have to actually raise them to some powers here also, right? So what is the probability of getting a defective egg raised to the power, it's going to be raised to the power since we're doing NC0, so it's going to be raised to the power 0, and the probability of not getting a defective egg would actually be raised to the power 10 minus 0. And if we solve it, we know that the probability of getting a defective egg is actually equal to 10%, which is 1 by 10. And that means the probability of getting a not defective egg is actually equal to 9 by 10, because the probability of success and failure, it will always add up to 1. So it's going to be 1 minus 10C0 is nothing but 1 into this over here, it's probability of defective egg, that is again something raised to the power 0, which is going to be 1, into this is going to be equal to 9 to the power 10 divided by 10 to the power 10. So my answer is actually going to be equal to 1 minus 9 to the power 10 over 10 to the power 10. So suppose you're understanding this point over here, guys, and let's just solve one more question. So I'll do this question freestyle with you. Let's suppose the question is that out of 10 balls, 4 balls are red, right? So 4 balls are red and 6 balls are blue. Let's say 6 balls are blue. And if let's suppose out of 10 balls, 4 balls are red and 6 balls are blue. 3 balls are, let's suppose 3 balls are drawn successively with the replacement, right? So 3 balls are drawn with a replacement. And the question is asking what's the probability of getting 2 blue balls. So the question is asking the probability of getting 2 blue balls. So in that case, that is actually going to be equal to the probability of getting 2 blue balls, and the number of drawns are actually 3. So the number of Bernoulli trials are 3. So it's going to be 3C2 into, and over here we have to, the probability of success is getting a blue ball. So getting the probability of blue ball raised to the power 2 here, and getting the probability of non-blue ball raised to the power 3 minus 2 here. So that is going to be 3C2, which is going to be 3 into 2 by 1 into 2, right? Whichever way you want to solve it, into probability of blue ball. So the probability of a blue ball is 6 by 10. So it's going to be 6 by 10 whole square into probability of not blue ball, which is going to be a red ball. That is actually 4 by 10 raised to the power 1. So that is going to be equal to 3 into 6 by 10 is going to be simply 2 times 3 and 2 times 5, which is going to be 9 by 25 into 2 by 5. So that is actually going to be our answer here, whichever way you want to solve it. But I suppose you're understanding this point here, guys, that this is something which is far more crucial than we solving any question. You have to understand this, that in a Bernoulli's trial, uh, the probability distribution follows the normal distribution, which means the probability of getting success x times is equal to ncx into the probability of success raised to the power x into probability of failure raised to the power n minus x. So that is something which is very, very important. In the future videos on probability, we would be solving some complex questions which will help you to understand this more practically, right? So before we see off, guys, this would be our our web address, that is perfect-scores.com. Don't forget to explore that. A lot of exciting stuff coming here. And this would be our Facebook page to give us your valuable like. That is facebook.com/perfectscores. And if you have any feedback to give me, you can always give me at perfectscores89@gmail.com. So this would be about this video, guys. Thank you very much for watching. I'll